Welcome back to an update about my MegaWang 2000 Turbo Edition hardware, which plugs into my Commodore 64. This is the schematic for my new super scaled sprites display layer. I'm calling it Sprites 4, and that's because there have been 3 other revisions of the sprites displaying layer. This is quite a large, complicated schematic. It mostly deals with the memory and register access for the display layer before it starts processing pixels, and also the logic which handles the calculation before the calculation results are handed over to the pixel display layer. There are 2 halves to this pixel display layer, and the difference from the previous scaled sprites is that this display layer uses a full frame buffer rather than 2 double buffered scan lines. This increases the amount of time that the scaled sprites logic has for rendering scaled sprites. It obviously increases it from just 2 double buffered scan lines to a full frame buffer, which is also itself double buffered. Now, when I run this in this Proteus simulation, schematic capture, and also simulation and PCB layout design tool, but I'm running the simulation. Now, sometimes it takes a little while to start up. Here we go. So the black screen is expected, and that's because there are 2 double buffered and initially cleared with effectively FF, which is all bits 1 in binary. There are 2 frame buffers, and they need to be cleared first of all before the logic can then start rendering sprite pixels into alternate frame buffers. So I have 3 scaled sprites in the test data. One is scaled up 4 times, one is normal scale, and one is scaled down by half. And the pixels are red, green, and blue, and then white, and then transparent. And the specific ordering of those colored pixels tells me whether or not all of the address decoding logic, all of the sprite flipping logic, and everything else is working. The test then goes on and waits for a vsync, or vblank rather, and then updates the sprite coordinates just to check to make sure that the sprite can traverse the most significant bit in the x coordinate and then go or straddle the MSBX coordinate on the screen. The difference between 255 and 256 and 257 in the horizontal coordinate range. Now, when I'm running this simulator, it can show me the contents of the RAMs. So these 2 larger windows are the contents of the frame buffer RAMs, and the 2 smaller windows on the left-hand side there just show the initial first few bytes of the sprite register RAMs. The sprite register RAMs are also double buffered because while it is calculating and displaying sprites from the on-screen and off-screen frame buffer, it will also pull information, and it allows the CPU, it allows the Commodore 64 to send data to the off-screen sprite RAM register list compared to where the hardware is accessing the on-screen RAM. Now, I've just run this in emulation here. So this window on the left is the emulated view, but the emulation actually outputs the all of the test data that it's sending through all of the emulated hardware. So I'm thinking, let's run this first time. I've not run this before yet. I've just been using the standard small test data, so I can tell the simulator to pick up the debug data that's saved out from the Java software-based emulation of this MegaWang 2000 Turbo Edition hardware stack. And whenever it runs, it can be instructed to output all of the bytes that are sent over, basically over the user port, and then the user port, all of the bytes that get sent to the video hardware. So it stores out a 24-bit address, and it also stores out the byte. And that's what those $D instructions are, or debug lines in the debug data output there. So the simulator, the digital simulator, Proteus, can because I've expanded it with my own data generation models, I can just tell it to consume that data file that's spat out by the emulation, and then to very slowly simulate all of the memory accesses that go on into the simulated, hardware simulated display hardware. And then it renders into this, again, simulated view on the right hand side. So let's see what we get. It should match the emulated view on the left with the simulated hardware view on the right. Again, we get 2 frames of black. This simulation view on the right hand side here is just basically a digital RGB display. It's not an analog display because I didn't want to have to bother with a full SPICE simulation. I just wanted to have a digital display for my RGB output, and wow, look at that. So the testing that I did with the test data seems to have worked really well, because it's just the hardware simulation has just basically rendered the frame correctly, apart from there seems to be extra data down at the bottom of that rotated water sprite. Let's just check the emulation, see what it sets up as. So I know that the sprite is, oh, okay, so in the sprite data that's been converted for the emulation demo, it's actually got all of that extra pixel data at the bottom of the sprite. So let's check what I'm doing in terms of sending bytes to the emulated video hardware in the test data setup. I'm initializing all of the combiner layers. Okay. The display is initialized. Ah, there we go. Okay, so the sprites for hardware, the super scaled sprites hardware, has the notion of clipping windows. So it has an origin and it also has extent values, which means that I can actually have like a clipping window that the scaled sprites can render into approximately. It's a good way of saving draw time. If the sprite hardware realizes that it's going to be rendering pixels outside of this clipping window, then it will just move on to the next sprite when it can, and it saves all of that time. So that's what I've done there. So if I run it with a larger clipping window, then there we go. It renders the bottom of the sprite data now in the emulated view. When I entered the value 80, that basically is multiplied by 2, giving a pixel height clip window of 256 bytes, 256 units in decimal, or 100 in hex. So 80 in hex is 128 in decimal. So 128 times 2 is 256. So now it's clipping inside a window which is 256 pixels tall, which is taller than the screen. So now if I rerun now the emulation on the left, you can see that the full water sprite, including all of the stuff at the bottom, is correctly there. And then of course the simulation, when it reruns that emulated memory transfer debug file, then it's also correct. So that's good. It means that the Java emulation matches with the hardware simulation, which is great. And the hardware simulation model for the display also saves out each full frame that it has received from the hardware simulation. So I can zoom in, and it's got the correct aspect ratio as well now. So I'm aiming for pixel accuracy, and I'm pretty sure if I expand the emulated window on the left to match the size of the output from the hardware simulation on the right there. So don't forget, this is the debug image from the hardware simulation on the right, emulation on the left. Let's just zoom that in a little bit more, scale it up. There we go. I think that's pretty much the same. And yeah, okay, yeah, the pixels look like they're all, and the important thing is that the sprites are all relative to each other as well. They are all displaying correctly as well. So that's fantastic, isn't it? Wow. First time running that test. first time running emulated data output in the hardware simulation and getting it to match. That's fantastic. Wow. Anyway, so there we go. There's the main control logic schematic again. So say, for example, this small complex area here dealing with S2 current sprite X pixel and then 0, 1, 2, 3, 4, 5, 6, 7. Those are all of the signals. Now, that corresponds to, in the Java emulation code, it corresponds to, and I've tried to use approximately the same variable name, it corresponds to, say, for example, this line here and also this line here. So current sprite X pixel gets set to an initial value, or every pixel it gets accumulated with the horizontal, the X scale factor for the scaled sprite. So this is internally, it is a 16-bit value which gets accumulated with progressively with 8-bit values. So there's an unsigned addition there going on. All of the adders and everything like that are 2's complement binary based adders as well. So the 2's complement mathematics for binary arithmetic tends to work out quite well. So I'm really happy with that test of the simulation. So what we can do now is that actually now the schematic for the sprites 4 display layer seems to be working relatively well. I've got to think now about actually getting this new board built and then tested. So there's a little bit more logic to go into this sprites 4 layer. The extent logic needs to get added if it's to match the software emulation, and I want to really try and match all of the feature set of the software emulation. So what we can do is that we can just add that extra logic later on, but I'm thinking just to really just do a test build of the PCB layout just to see what it looks like, to see what the overall size of the final board's going to be. So I'm just setting the group of all of the components used on the 2 schematic sheets. And that's because I want to tell the autoplacer in this design tool to place all of the integrated circuits, all of the components that are tagged with sprites 2. I'm not going to rename it to sprites 4 yet in the design, but I guess I'm going to have to at some point. So sprites 2 was the scaled sprites, but scanline buffered scaled sprites. So the scanline rendered scaled sprites, which was okay, but it certainly ran out of the ability to render sprites. So this is the autoplacer in the tool. I tend to use the autoplacer and the auto router a lot, and that's because I tend to iterate quite a lot on testing new hardware designs in this Proteus simulation tool first. And to be honest, laying out, 196 components by hand is a time-consuming job. And I'm not going to do that because I want to test quickly my new hardware designs. Now, because this only runs at something like 12, 14, maybe 16 megahertz, I don't need to worry too much about signal issues and stuff like that that you would tend to get with higher speed electronics. So generally all of my boards work fine with autoplace and auto route. So I've changed my designs to use these surface mount components now, mostly. Some of the RAMs still use through hole, but mostly the design will use surface mount chips these days. So this is going to take a while. I might pause the video here and come back to it later on when it has finished doing its auto route. One moment, please. So here we are back again. It's almost finished, and there we go, it's completed. So all of the yellow arrows basically indicate how far or where the ideal position for the components are in relation to their schematic connections. So the auto router tries to shorten those yellow arrows as much as possible, I guess. It takes quite a while. But this is what the board looks like, populated but not routed. So you can see that there's no traces in the 3D visualizer, but we can see pretty much all of the packages that are going to be used for the components. So there are some surface, some through hole, but mostly surface mount components now. We can spin the board around, we can have a look, we can see how things fit together. This board is approximately, what was it? About 200 millimeters by 210 millimeters. So 20 centimeters by 21 centimeters approximately. I'm just going to, for the auto routing, I'm just going to set up 8 layers with more signals and then just see how it routes. Now, some are going to say, well, where are your power planes? Where is your signal isolation? And to that, I'm just going to say, well, this is just a test route. I want to see if 8 signal layers is going to be enough to have this correctly route with this board size, with this component density. Now, each of the layers, even though they are all tagged as signal layers, I did add the some power planes, but the power planes can get chopped up by signals that get generated. So all of that looks good. I'm just double checking all of my settings. There's the rat's nest turned on, so we can see the green rat's nest there was showing the complexity and the density of the intended connections between the components. So let's just sit back and wait for the auto route to complete. This is going to take quite some time because it's a very complex operation. So one moment, please. I will be back when it's finishing. I can see it's got to 5 conflicts now, so it's just about to finish. The conflicts are down at the bottom and beside the progress bar, 84%, 86%, 88%. It does numerous passes to try and solve the routing. You can see from all of the traces here that it's a very complex interconnected design. There we go, 0 conflicts. That's what I'm looking for. It now means that instead of 1,769 missing connections between the components, there are now 0 conflicts, which means it has successfully created traces in the PCB layout for all of those missing connections. So the missing connections is basically missing connections in terms of PCB traces compared to the schematic connectivity data, which is rendered as a rat's nest. So it's just going through the cleanup pass now. It's cleaning up the traces and it's cleaning up the vias, making sure all of the stuff is nice and tidy. This can also take quite some time. I'll come back later when it's really done. Okay, Welcome back, and now it's really done. So we can see the complexity of this board. If I open up all of the layers and then we switch off all the layers, and then we can have a look at the individual copper layers, the top copper, the bottom copper, and the inner layers. We can see the signal density for the inner layers, but we can also see where these power planes have maintained much of their coherency. So actually mixing the signals and the power planes isn't too bad, really. There's still going to be some signal integrity guards from these partial power planes. Some of them are tied to ground, some of them are tied to positive voltage. So we can see here that when I turn on all of the inner power planes, you could see that there was most of the PCB copper area covered. So now if we go to the 3D view, we can see the traces on the front and the back. And it looks a lot better right now. I'm very pleased with this board, how it looks. It's actually, using surface mount components, it's actually the same size as pretty much as the through-hole version of the previous version of the scaled sprites layer. And of course, the previous version of the scaled sprites layer is not as complex. The previous version of the sprites layer only had 32 by 32 pixel scaled sprites. It didn't have variable width and variable height, for example. It didn't have so much memory. It didn't have the notion of clipping windows and stuff like that. So, I'm really happy that this board has turned out like that. Now I have to make some decisions on how many signal layers I'm going to really use, how many power plane layers I'm really going to use, and where those power plane layers are going to go to help signal integrity and all of that kind of stuff, and whether or not it's going to be better to make a board with more layers but smaller size, or larger size and fewer layers, because if you spread out the components, then you don't need so much signal density. Anyway, so I'll leave this video there. There's already quite a lot to go through. This is just a short update about my super scaled sprites 4 display layer for my MegaWang 2000 Turbo Edition hardware, which plugs into my poor little Commodore 64. I hope you enjoy these technical videos. If you like this kind of thing, then please do consider liking or subscribing to my channel, and I hope to catch you around next time. Take care, have a great day, evening or night, wherever you are.